To compute the determinant of a 5 by 5 matrix by cofactor expansion, you need to evaluate 120 terms, and that's 5 factorial. But elimination gives the same answer in roughly 15 arithmetic steps. That's exactly what every computer does. Here's the idea. Elimination converts any matrix into upper triangular form. Then you simply multiply the diagonal entries. That product is your determinant. And let's see why this works and build a complete algorithm for any matrix. It starts with one key fact about triangular matrices. But first, let's recall the tools. The determinant is pinned down by 3 foundational properties. Property 1, the determinant of the identity matrix is 1. Property 2, a row swap flips the sign of the determinant. Property 3, the determinant is linear in each row. From these 3 properties, 2 important consequences follow. Property 5, adding a multiple of one row to another does not change the determinant. And this is the raw replacement operation, the backbone of Gaussian elimination. And property 3a, factoring a scalar out of one row multiplies the determinant by that scalar. And these 2 facts, row replacement preserves the determinant and scalar factoring multiplies the determinant, drive everything that follows. Take a 3 by 3 upper triangular matrix. An upper triangular matrix has all zeros below the main diagonal. Ours has diagonal entries D1, D2, D3, and arbitrary entries above the diagonal. Now here is the key argument. Step 1, use row replacement to zero out the entries above the diagonal. We subtract appropriate multiples of lower rows from upper rows. By property 5, each of these row replacement steps leaves the determinant unchanged. The result is a diagonal matrix with D1, D2, D3 on the diagonal, and the zeros everywhere else. Step 2, factor D1 out of row 1, D2 out of row 2, and D3 out of row 3. Property 3, it says each scalar factor pulls out as a multiplier of the determinant. What remains after factoring is the identity matrix, and the property 1 tells us the determinant of the identity matrix is 1. So putting it all together, the determinant equals D1 times D2 times D3, the product of the diagonal entries. Let's see a concrete example. Consider the upper triangular matrix with rows 2, 3, 1, then 0, 5, 4, then 0, 0, 3. Its determinant is simply 2 times 5 times 3, which equals 30. This argument works for any n by n triangular matrix, whether upper or lower. Let's verify our result with the 2 by 2 case. Start with a general 2 by 2 matrix with entries A, B, C, D. We subtract C over A times row 1 from row 2. The new row 2 becomes 0 and D minus CB over A. By property 5, this row replacement does not change the determinant. Now the matrix is upper triangular. We multiply the pivots times the quantity D minus CB over A. Simplifying, the A in the denominator cancels, and we get AD minus BC. That's exactly the standard 2 by 2 determinant formula, derived purely from elimination. Now let's do a numerical check. Take the matrix 3, 2, 6, 5. The multiplier is 6 over 3, which equals 2. Subtract 2 times row 1 from row 2. Row 2 becomes 0, 1. The pivots are 3 and 1. Their product is 3 times 1, which equals 3. As a separate check using the direct formula, 3 times 5 minus 2 times 6 equals 15 minus 12, which equals 3. It matches perfectly. Most matrices aren't triangular, so here's the complete algorithm for computing determinants. Step 1, perform Gaussian elimination on matrix A to reach upper triangular form U. A pivot is the leading non-zero entry in each row after elimination. This step is justified by property 5, row replacement operations don't change the determinant. Step 2, count every row exchange you performed during elimination. Call the total R. This matters because of property 2. Each row exchange flips the sign of the determinant. Step 3. Compute the determinant as -1 to the power r times the product of all pivots. Why does this work? After elimination, the upper triangular matrix U has the same determinant as A up to sign. Multiply the diagonal entries of U, those are the pivots, and apply the sign correction from the row swaps. Now let's trace through the algorithm as a flowchart. Start with matrix A. Perform elimination. If a row swap is needed, increment R and continue eliminating. If no row swap is needed, keep going. But if you encounter a 0 pivot and no swap is available, the determinant is 0. You're done. Otherwise, once you reach upper triangular form U, compute the determinant as -1 to the power r times the product of all pivots. Let's work through an example that requires a row swap. Our matrix A has rows 0, 2, 1, then 3, 1, 2, then 1, 0, 3. Notice the top left entry is 0, so there's no pivot available in that position. We need to swap rows 1 and 2. After the swap, row 1 becomes 3, 1, 2, and the matrix is now 3, 1, 2, then 0, 2, 1, then 1, 0, 3. We've done one exchange, so R equals 1. Next, subtract 1/3 of row 1 from row 3. Row 3 becomes 0, -1/3, 7/3. Now we need to eliminate the entry in row 3. Column 2, add 1/6 of row 2 to row 3. Row 3 becomes 0, 0, 5/2. We've reached upper triangular form. The pivots along the diagonal are 3, 2, and 5/2. Their product is 3 times 2 times 5/2, which equals 15. Since we performed one row exchange, the sign flips once. The determinant equals -1 raised to the power 1 times 15, which gives us -15. This reveals a deep connection. The determinant of A equals 0 if and only if A is singular, meaning not invertible. Let's see both cases side by side. On the left, consider the invertible case. Take the matrix with rows 2, 1, 0, 1, 3, 2, 0, 1, 4. When we reduce this to upper triangular form, we get non-zero pivots, 2 5/2 and 16/5. Since every pivot is non-zero, their product is non-zero and the determinant is not 0. On the right, consider the singular case. Take the matrix with rows 1, 2, 3, 4, 5, 6, 7, 8, 9. When we reduce this, the bottom row becomes all zeros, giving a 0 pivot in the 3, 3 position. A 0 pivot means the product of all pivots is 0, so the determinant equals 0. Here is the key logic. If A is singular, elimination must produce a row of all zeros. A 0 row means a 0 pivot, so the product of pivots is 0 and the determinant is 0. Conversely, if A is invertible, every pivot is non-zero, their product is non-zero, and the determinant is non-zero. The bottom line is elegant. The determinant of A equals 0 if and only if A is singular. The determinant gives a clean binary test for invertibility. Now let's appreciate the enormous efficiency gain that elimination provides. Cofactor expansion requires on the order of n factorial operations. Elimination requires only on the order of n cubed. Let's compare these side by side. For n equals 5, cofactor expansion takes 120 operations, while elimination takes 125. And they're actually comparable at this small size. But watch what happens as n grows. For n equals 10, cofactor expansion requires 3,628,800 operations. That's over 3.6 million. Elimination requires just 1,000 for the same matrix. For n equals 20, cofactor expansion explodes to approximately 2.4 times 10 to the 18th power. That's 2.4 quintillion operations. Elimination, just 8,000. And for a 100 by 100 matrix, cofactor expansion demands approximately 9.3 times 10 to the 157th power operations. That is more steps than there are atoms in the entire observable universe. Meanwhile, elimination needs only about 1 million operations. And this dramatic difference is exactly why every serious numerical library computes determinants through elimination, not cofactor expansion. Here's the full picture. We've built a mechanical efficient algorithm for computing determinants. The master formula is the determinant of A equals -1 raised to the power R times P1 times P2 times ... times Pn. That is, perform Gaussian elimination, track your route swaps to get R, multiply the pivots together, and apply the sign. Now the determinant serves three fundamental roles. First, it is a volume scaling factor, telling us how a linear transformation stretches or shrinks space. Second, it is an invertibility test. The matrix is invertible if and only if the determinant is non-zero. Third, it is an algebraic formula, a polynomial expression in the entries of the matrix. And Gaussian elimination beautifully bridges all three of these perspectives. Next time, we'll see how this product of pivots idea leads to an elegant factorization. The determinant of A equals the determinant of L times the determinant of U.